All right, so this is just what I said. We force the control value in the IDEX register to 0. Okay, so that means all the following stages, they are essentially doing nothing. And we prevent update of PC and the IFID register. So that means the same instruction will be decoded again. Okay, so if we have a load word followed by an end, the hazard detection module will find that this RT in the load instruction is the RS in the end instruction. So here, this instruction becomes no operation. So we will do an instruction fetch here, but we will fetch the same thing again at the next clock cycle. Okay? All right, so let's look at what's inside. I'm sorry. All right, so let's look at what's inside the CPU. So at the first clock cycle, of course, we need to fetch the lower instruction. And the clock cycle 2, we do the instruction decode. And simultaneously, we fetch the next instruction, which is the end instruction. All right, so here, instruction decode, so we will set the control signals for this instruction. And we will put the RS, RT, RD, and the immediate fields all to what they are needed. At the next instruction, the low word is in its execution stage. The end instruction is in its decode stage. And here, this hazard detection unit will find that this lower instruction, the RD of this lower instruction, I'm sorry, the RT of this lower instruction is the RS of this end instruction. So it knows that we have to wait. Okay, so it will set the PC write as 0, and it will set this IFID write to be 0. And not only that, it will set all the control signals to be 0. Okay, so at the next instruction, the low word is in the memory access stage. But in the in the third stage here essentially the CPU is doing nothing because all the control signals are 0. Okay, it's doing nothing. And here we are doing the end again. Okay, because this instruction fetch and decode, this register, its value is still the same as the previous value. Right, so it's doing the end again. Not only that, this PC is still the same as the previous clock cycle. So it will fetch the same instruction again. Okay? And now, because the previous instruction is essentially sort of like bubble. So this hazard detection unit will find that there's no hazard in the current situation, right? Because the previous instruction is essentially just bubble. So of course the RT doesn't equal to the RS or RT here. Okay? So in the next clock cycle, the end will go here. And now, this hazard detection unit, it will find that we have 2 consecutive R-type instructions. And the previous RD is the current RS. Okay, so there will be a hazard. But we don't need to wait, we just need to do a forwarding. Okay, so this $4 will be forwarded. Not only that, this low word it hasn't been written to the $2 yet. right? So this hazard detection unit, it will also detect another hazard, which is this lower instruction is RT equals to the RT here, right? So this value here also need to be forwarded here. I'm sorry, let me check it. Let me check it's correct or not. I'm sorry, let me make some correction. I sort of explain clock cycle 5 and clock cycle 6 simultaneously. So let me say that again. At clock cycle 5, there's a hazard, but this hazard happens only between this instruction and this instruction. Okay, the lower here has to be forwarded to as the first input here. Okay, that's what happened in the 5th clock cycle. This unit, it will detect a data hazard between this end instruction and this lower instruction. Okay, so we need to forward this $sign, the value from here to here. And at clock cycle 6, we will find another data hazard, which is this, the RD of this end instruction and the RS of this OR instruction. Okay, so we need to forward from here to here. Okay, and then the next instruction. So here we have two different data hazard. One is between this $4 and this $4 here. One is between this $4 and this $4. Okay. So if we have 3 consecutive R-type instructions, and the RD of the previous 2 instructions is the RSO RT of the current instruction, then in this case we need to forward the latest value to this add. Right? We have $4 here, we have $4 here. So we should forward this one to here, right? Because this is the latest result, right? So that means we need to forward this one to here. Okay, so let me summarize again. If we have 3 consecutive R-type instructions and the RD of the previous 1 and previous 2 instructions is the RS or RT of the current instruction, we need to forward the previous RD to the current RS or RT. All right, so that's all about the data hazard. And the data hazard can also be avoided via code scheduling. So this is something that can be done within compiler instead of in. So we talk about how to avoid data hazard in CPU, but data hazard can also be avoided from compiler. So if somehow, so here we have a load word here and then add. So here the RT equals to the RT here. So if based on our previous discussion, we know that we need to do not only the data forwarding, but also we need to wait for 1 clock cycle if we have a load use data hazard. Likewise, here we have another data hazard. This T4 is the T4 here. But if somehow the compiler is smart enough to reschedule the code in this way, then we don't need to wait. So if the logic is still the same, but we don't need to wait. Okay. So without the code rescheduling, after 5 clock cycles, we will finish the first instruction, right? And after 6 clock cycles, we will finish the second instruction. But the third one is finished 2 cycles later because we need to have we need to wait for 1 extra clock cycle. right? So after 5 instructions, after 5 clock cycles, we finish the first one. 6 clock cycles, we finish the second one. After 8 clock cycles, we finish the third one. And 9, 10. And here, after 12 clock cycles, we finish this one. And after 13 cycles, we finish all these instructions, right? But if we reschedule the codes, then we only need 11 clock cycles. After 5 clock cycles, we finish the first instruction. And after that, every clock cycle will finish 1 extra instruction. So in total, we need only 11 clock cycles. All right, so I talk about this simply. I simply want to let you know that a good compiler needs to know, or a good compiler also needs to know how the CPU is designed, how the instruction set architecture is designed, so that it knows perhaps it needs to switch certain code schedules to improve the throughput. All right, so stalls essentially is no operation, so it reduces the performance, reduces the throughput, and forward can partially reduce the data hazard, but sometimes we still need to wait. And compiler can also rearrange the code to avoid certain data hazards. All right, so for data hazard, we said that there are 2 types of data hazard. Here, the 2 types means that one is the consecutive R-type instructions. One is the load use instruction. And we said that we have the read after write, write after read, and write after write data hazard. But in MIPS, we only have the first one. If the hazard is because of the memory load, then we need to stall, because otherwise we just cannot get the right value.